Imagine for a second that you just hired like a brilliant new assistant to manage your inbox, your schedule, and basically all your daily operations.
Okay, sounds great so far.
Right. I mean, they are incredibly smart. They're capable of understanding complex instructions, and they're lightning fast.
Yeah, the dream assistant.
Exactly. But there is a massive catch.
Oh, there always is.
Every single morning when they walk into the office, their memory is wiped completely blank.
Oh, wow.
Yeah. They have absolutely no recollection of what they did yesterday, what your preferences are, or, how your company's internal software even works.
That sounds like a nightmare.
You literally have to teach them your entire workflow from scratch every single day.
I mean, it sounds incredibly exhausting. You would spend more time managing that assistant than you would actually doing your own work.
Exactly.
The friction would just totally negate all the benefits of their intelligence.
And the wild thing is, that is exactly how most artificial intelligence operates right now.
Yeah, it really is.
When you use an AI agent to do a complex task, it's essentially a temp worker trapped in the movie 50 First Dates.
That is a very accurate and depressing analogy.
Oh, welcome to this deep dive.
Yeah.
Today, our mission is exploring a massive leap forward in AI capabilities.
It's a really exciting topic.
It is,
Yeah.
because we are looking at how artificial intelligence is finally moving from being this, amnesiac executor to a self-evolving worker that literally learns on the job.
Which is huge for anyone using these tools.
Absolutely. We're drawing on state-of-the-art foundational materials highlighted by the Generative AI Foundation papers, and we are specifically focusing on a groundbreaking new framework called MUSE.
Right, MUSE.
Okay, let's unpack this because we really need to define the gap between what we think AI can do and why it fours at your actual day job.
Yeah, there's a big disconnect there.
Because we see these headlines all the time, right? About AI passing the bar exam or writing complex code, but then you ask it to, organize a project folder and it completely falls apart.
It's so true, and it really comes down to how we benchmark AI.
How do you mean?
Well, historically, we've tested these agents in simulated environments, things like Webarena or Osworld.
Okay.
And those are useful tools, don't get me wrong.
Right.
But they typically evaluate isolated functionalities within a single platform.
Right, like a controlled lab experiment.
Exactly. We're talking about short horizon tasks, maybe 20 steps long at most.
So things like finding a product, putting it in a cart, checking out.
Yeah, exactly that. But real-world productivity is a completely different beast.
Oh, for sure. Real work is messy.
Very messy.
But it's never just 20 clean steps on one clean website.
No, not at all. Real-world productivity tasks involve long horizon planning. I mean, they can require 100 or more steps.
Wow, 100 steps.
Easily. And crucially, they require fluidly switching across multiple applications.
Right, which AI usually hates doing.
Exactly. Think about your own workflow, right? You might get a message in a chat app like Rocket Chat, and then you have to search for a report in your cloud storage, maybe OwnCloud. Then you have to extract data from a PDF and finally process that data in a code editor.
Yeah, that's just a standard Tuesday.
Right. But current models struggle here because they are what researchers call test time static.
Test time static.
Yeah.
Meaning they are essentially frozen in amber the moment they leave the lab, right?
Yes, exactly.
Their learning completely stops the second their initial training is finished.
That is the core issue right there. Once they are deployed, they just don't learn from their daily interactions.
Okay.
So if an AI agent makes a mistake navigating a complex corporate system on Tuesday, say, I don't know, clicks the wrong subfolder in your cloud storage.
It will make that exact same mistake on Wednesday.
Precisely. It repeats errors on repetitive tasks because neither its successes nor its failures are consolidated into actionable knowledge.
Wait, I have to push back on this a little bit.
Sure.
Aren't foundational models like GPT-4 already incredibly capable?
Oh, definitely.
I mean, they have ingested practically the entire internet. Why can't a massive, highly trained model just power through a 100-step task right out of the box using all that pre-existing knowledge?
This raises an important question, actually, and the answer gets to the core of how intelligence actually operates in practice.
Okay.
Because human experts don't solve complex, multi-step problems through raw, instantaneous processing power alone.
We don't just calculate the answer instantly.
Right. We rely heavily on memory, context, and trial and error.
Oh, absolutely.
When you face a 100-step task, you are constantly checking your current work against your past experiences.
Like, did this work last time I tried it?
Exactly.
Yeah.
But without memory, an AI agent operates without a safety net.
Because it's trying to hold the entire context of a massive task in its immediate short-term processing window.
Precisely. It's too much to juggle. If it makes a tiny contextual error on, say, step 12, that error compounds.
It snowballs.
Right. It doesn't realize it took a wrong turn, so it builds its next action on a flawed premise.
Oh, man.
By step 40, it's hallucinating entirely new information just to make sense of the mess it made.
And by step 80, the entire task just collapses.
Totally collapses.
So throwing more computing power at the problem doesn't fix the lack of a workflow.
No, it really doesn't.
Because raw processing power isn't the answer. Researchers realized they had to build a system that actually mimics human workflow.
Yes, a totally different paradigm.
And that brings us to the MUSE framework, which stands for Memory Utilizing and Self-Evolving.
It's a brilliant shift in perspective, honestly. Instead of trying to build a bigger brain, the researchers built a better system for the brain to operate within.
I like that.
The core mechanism of MUSE is an experience-driven, closed-loop system.
Okay.
It operates on what they call a plan, execute, reflect, memorize loop.
Plan, execute, reflect, memorize.
Exactly.
So if we look under the hood of this framework, how is it actually built? Because it can't just be one big prompt telling the AI to try harder, right?
No, definitely not. It's actually a dual agent setup.
2 agents.
Right. It starts with the planning execution agent, or the PE agent.
The PE agent, okay.
This is the part of the AI that actually gets its hands dirty. When it gets a big task, it breaks the main objective down into an ordered queue of subtasks.
Just making a to-do list.
Exactly. And to execute those subtasks, the PE agent uses a minimal usable toolset.
Now that feels like a very intentional design choice.
Oh, it absolutely is.
They didn't give the AI thousands of specialized APIs for every software under the sun.
Right.
They gave it a web browser, a Python interpreter, a shell, a vision extractor so it can visually see what's on the screen,
Yeah.
and a memory retriever.
A very stripped-down toolkit.
Right. It has to creatively combine those basic tools to get things done rather than just pressing a magic pre-programmed button.
Which forces it to actually problem solve.
Yeah. But the PE agent is only half the equation, right?
Yes, the PE agent acts, but the real magic of the MUSE framework is the reflect agent.
The reflect agent.
Right, the reflect agent acts as an independent third-party supervisor.
Oh, I love this. It's exactly like a classic corporate dynamic.
It really is.
The PE agent is the eager intern. They are doing the grunt work, clicking the buttons, writing the code, just trying to get the task done.
Sweating over the keyboard.
Exactly. But the reflect agent is the meticulous manager sitting at the desk across the room reviewing the intern's work.
That separation of duties is key.
Right.
The manager isn't doing the clicking, the manager is evaluating the outcome. And it does this against 3 specific dimensions.
Okay, let me guess what a robotic manager would actually check for. I assume the first thing is just making sure the intern isn't making things up.
You nailed it. That is the first dimension. Truthfulness.
Truthfulness.
The reflect agent uses that vision extractor you mentioned to look at the screen and verify that the intern's conclusions are grounded in actual feedback from the environment.
So it's checking that it's not just hallucinated text.
Exactly. It has to be real.
And then I'd imagine it checks if the actual work is done. Like,
Yeah.
does this file exist?
Right again. That is the second dimension. Deliverable verification.
Makes sense.
It literally checks the system to see if the output file or the requested report is present and complete.
And the third dimension.
The third dimension is data fidelity.
Oh, okay.
Confirming the intern didn't accidentally overwrite, lose, or, alter critical data during the process.
Because you don't want the intern deleting the company database while trying to format a spreadsheet.
Exactly. Data fidelity is crucial.
What's fascinating here is how autonomous the evaluation process is.
Oh, it's completely hands-off for the user.
Right. There is no human holding the AI's hand, looking over its shoulder to say, hey, you missed a spot.
Not at all.
If the eager intern fails a subtask, the reflect agent doesn't just crash the program with a generic error code.
Which is what we're used to.
Right. Instead, it generates a detailed diagnostic failure analysis.
It gives feedback.
It actually forces the intern to replan and try again, specifically encouraging them to explore new methods rather than just clicking the same broken link over and over.
And if the intern actually succeeds, The reflect agent takes that successful execution trajectory, so the exact sequence of steps that worked, and translates those raw actions into a structured, reusable experience.
But a performance review is useless if it's thrown in the trash, right?
Totally.
Where does the manager's feedback actually go so the intern doesn't make the same mistake tomorrow?
Well, it goes into what the researchers call a highly structured, three-tiered memory module.
Three-tiered memory module.
Right. This is the agent's evolving brain.
Okay, structuring it into 3 distinct tiers. Why 3?
Because it allows the agent to organize diverse levels of knowledge, from very granular physical actions all the way up to high-level conceptual strategies.
Okay, let's look at the first tier, tool memory.
Right, tool memory.
Which is essentially the agent's muscle memory, right?
That is the perfect analogy. It operates almost automatically. It's the foundational knowledge of how to properly invoke a tool.
Like using a hammer.
Exactly. Before the agent acts, it pings the memory retriever. If it needs to use a browser, the tool memory provides the static description of the browser's core functionality,
Okay.
along with dynamic instructions guiding the exact syntax needed to perform, say, a click or a scroll.
Okay, so tool memory gives the agent its basic muscle memory. But knowing how to click a mouse doesn't mean you know how to file an expense report.
No, it definitely doesn't.
So how does it learn the actual multi-step workflow?
That brings us to the second tier, which is procedural memory.
Procedural memory.
Right. This acts as a hierarchical knowledge base of standard operating procedures, or SOPs.
Okay, so the actual step-by-step instructions for a specific job.
Exactly. And the paper provides excellent examples of this. An SOP in the procedural memory might detail exactly how to navigate to the login page of the Rocket Chat app,
Okay.
and how to handle potential server timeouts, input the credentials, and verify the login was successful by checking the post-login user interface elements.
Wow.
Another SOP might document the exact path to locate a specific folder in the OwnCloud storage system and confirm the presence of expected files.
So it's basically writing its own user manuals based on its own successful attempts.
Yes, it writes the manual, it pings the memory retriever, pulls up the manual, and follows its own steps.
That's incredible. And then there's the third tier, strategic memory.
Right. This focuses on high-level macro paradigms.
Macro paradigms. What does that mean?
It's distilling the lessons learned from major dilemmas the agent faced.
Okay.
So it moves beyond how to click a button or how to log in and tackles how to approach a complex problem.
What did that look like in practice, though?
Well, the researchers highlighted some fascinating examples. For instance, the agent organically learned a principle called systemic root cause.
Systemic root cause.
Yeah. If it encounters recurring errors in a task, the strategic memory instructs it to stop treating the immediate symptom and actually diagnose the underlying systemic cause.
Just to ensure long-term stability.
Exactly. Another derived strategy is adaptive task progression.
Okay.
This tells the agent that if its initial operational path is blocked, it shouldn't just crash. It needs to dynamically implement fallbacks and provision whatever prerequisites are missing.
Now, here's where it gets really interesting.
Oh, yeah.
I was reading through the structure of this memory module, and all of this memory, the tool memory, the SOPs, the strategic paradigms, it's all stored in natural language.
Right, plain text.
It's just plain English text, not code, not weights. Why is that such a monumental shift?
Because the memory is stored in natural language, it is completely LLM-agnostic.
LLM-agnostic.
Yes, it is decoupled from the underlying base model that originally generated it.
So we aren't talking about mathematically rewiring the AI's core brain, its neural network weights.
No, not at all.
We are talking about a complex brain transplant.
Exactly. Think of it like a highly indexed, searchable PDF manual.
Okay.
You could have a lightweight, incredibly cheap AI model run through thousands of tasks.
Like an entry-level worker.
Right. It makes mistakes, learns the ropes, and builds up this massive library of plain text SOPs.
Yeah.
Then you can take that entire text-based memory module and just hand it over to a completely different model.
You could just pass that written manual over to a powerful open source model, like, say, DeepSeek V3.
Exactly.
The new model just reads the relevant text via its context window or a retrieval system, and its capabilities are instantly boosted on day one.
Right. And that portability changes the economics of the entire field.
How so?
Because you aren't locked into the proprietary ecosystem of whichever tech giant built the model that generated the experience. You are building a portable asset.
Portable corporate brain.
Yes.
Okay, so we have a plan, execute, reflect, memorize loop feeding a 3-tiered natural language memory system.
Right.
But theory is one thing. How does this agent actually perform when you drop it into a simulated chaotic corporate environment?
To test that, the researchers used the TAC benchmark.
TAC.
Yes. TAC stands for the agent company. It is a rigorous, high-fidelity simulation of a corporate environment containing 175 deeply complex tasks.
Wow.
And they span 6 core corporate roles, things like human resources, project management, and software development.
And these aren't simple tasks. They require an average of over 40 action steps.
Exactly.
And usually require the agent to jump between different software platforms.
It's very demanding.
The paper detailed 2 specific case studies from this benchmark that perfectly illustrate how MUSE goes beyond just following a rigid script.
The case studies are amazing.
The first one is a human resources task, and it is genuinely funny to me.
Yeah, this one is great.
The objective given to the agent was to collect performance feedback on an employee named Lu Qiang.
Okay.
The agent needed to get this feedback from 3 specific colleagues: Mike Chen, Li Ming, and Zhang Wei.
Right. Now, the standard approach, the one the benchmark actually expected the AI to take, would be sequential.
One at a time.
Exactly. The agent would open a chat with Mike, ask for feedback, wait for a response, then open a new chat with Lin, and so on.
But the MUSE agent looked at that plan and basically decided it was terribly inefficient.
It really did.
Instead of having 3 separate, time-consuming one-on-one conversations, the agent independently navigated the chat software, created a brand new multi-person chat group containing all 3 colleagues, and asked them all at once.
It's brilliant.
It massively streamlined the information collection process. The AI essentially found a corporate life hack by organizing a group chat to save time.
It's so funny. And if we connect this to the bigger picture, it shows genuine adaptive problem solving.
Yeah, it didn't cheat.
No, it didn't break any rules at all. It just found a more efficient operational sequence that a rigid, script-following AI would never have discovered.
That's wild.
Yeah.
And the second case study shows that adaptive path progression strategy we talked about earlier in action.
Yes, the project management one.
Right. So the goal was to assign a new issue in a GitLab project called Rising Wave to a developer named Li Ming. So the agent navigates to GitLab, finds the project, starts to create the issue, and tries to assign it to Li Ming. But there's a problem.
Big problem.
Li Ming isn't registered in GitLab. The benchmark creators intentionally didn't give him an account.
Right. A traditional AI agent would just hit that wall, fail the task, and return an error message saying user not found.
Because it lacks the capacity to resolve missing prerequisites.
Exactly.
But the MUSE agent dynamically pauses.
This is where the magic happens.
The reflect agent kicks in, recognizes the dilemma, and instead of giving up, it initiates an entirely new sequence of subtasks.
It adapts.
The agent navigates the GitLab admin panel. It creates a brand new user account for Li Ming. It sets up his profile.
Unprompted.
Completely unprompted.
Yeah.
Then it navigates back to the Rising Wave project, adds the new Li Ming account to the project as a developer so he actually has permissions, and then finally assigns the issue to him.
It orchestrated nearly 20 subtasks and performed over 100 actions autonomously.
Just to solve a problem that wasn't even in its original instructions.
Exactly. It recognized a blocked path, dynamically provisioned the missing prerequisite, and completed the objective.
Just like a resourceful human employee who realizes a new hire isn't in the system and takes the initiative to add them rather than just giving up for the day.
Exactly. It's real agency.
The agent is clearly resourceful. But do the hard numbers actually back up these anecdotes?
The performance metrics are undeniable, honestly. When tested on the full TAC benchmark of 175 tasks, MUSE hit an average partial completion score of 51.78%.
Wow, over 50%.
Right. To put that in context, this is the first time any agent has surpassed the 50% threshold on this benchmark.
Oh, wow.
It represents a massive 20% relative leap over the previous state-of-the-art.
Which was held by who?
Claude 4 Sonnet.
Okay, and the incredible part to me is the model they used to achieve this. Because they didn't use the biggest, most expensive model on the market.
Not at all.
They achieved this 20% leap using the lightweight Gemini 2.5 Flash model.
Yeah, that's the kicker. They proved that a smaller model equipped with an evolving memory system can vastly outperform a heavier, more computationally expensive model that lacks the ability to remember.
That is huge. And they also ran continuous learning experiments, right?
They did.
They just let the agent run through tasks iteratively to see if it actually improved over time without any human engineers tweaking its code.
Yes. They set up 3 sequential iterations, and the results were a steady, uninterrupted upward trajectory in performance.
So it actually got better on its own.
Significantly better. In the first iteration, the agent scored around 55%. By the third iteration, just by accumulating procedural and strategic memory from its own experiences, its performance grew to over 66%.
Just by practicing.
Exactly. And perhaps most impressively, they tested the agent on a subset of ultra-hard tasks that it had never seen before.
Right, tasks where models usually score near zero.
Yeah.
They wanted to see if it was just memorizing the specific answers to the test, or if it was actually learning transferable skills.
Exactly. They were testing its ability to tackle completely unseen problems based on its past experience.
And how did it do?
When equipped with the memory it had built up, its performance on those never-before-seen ultra-hard tasks jumped significantly.
Which proves the agent is learning generalized problem-solving paradigms, not just rote memorization.
Exactly. It is actually learning how to work.
So what does this all mean? Are we basically saying that a smaller, lightweight model with a good notebook can beat a massive genius-level model that has amnesia?
That analogy captures the essence perfectly. It really does, and it validates a profound implication for the future of artificial intelligence.
Which is?
Well, for a long time, the industry consensus was that we just needed to keep training infinitely larger foundational models. Just feed them more data, give them more parameters.
Bigger is better.
Right. But the MUSE framework demonstrates that scaling raw parameters isn't the only path, and perhaps not even the most efficient path, to true autonomous agency. The future is about giving these models the architectural scaffolding to reflect on their actions, structure their experiences into a natural language manual, and basically self-evolve.
Let's recap this journey for you, the listener. We started by looking at the core frustration of current AI, that it acts like an amnesiac executor, failing at complex real-world productivity tasks. Because a tiny error at step 12 turns into a massive hallucination by step 40.
Right.
We explored how the MUSE framework solves this by introducing a plan, execute, reflect, memorize loop.
The core engine.
Exactly. The eager intern does the work using basic tools, and the meticulous manager reflects on the outcomes, checking for truthfulness, deliverables, and data fidelity.
And we broke down how those reflections aren't just thrown away.
Right, they go into the memory.
They are stored in a 3-tiered natural language memory system. The agent builds a library of basic tool use, complex standard operating procedures, and high-level strategic paradigms.
Which is just incredible.
This architecture transforms AI from static, frozen tools into dynamic, self-evolving agents capable of navigating highly complex, 100-step corporate environments.
And this is going to have a direct impact on your life and how you work. Soon, the AI tools you use won't just blindly execute your prompts and forget you exist the moment you close the window.
Thank goodness.
Right. They will actively learn your unique organizational systems. They will remember your preferences. They will proactively figure out workarounds when a file is missing or a login fails, because they will have built an internal manual of how you do business.
It bridges the gap between the promise of artificial intelligence and the reality of your daily productivity.
But I want to leave you with one final mind-bending idea to ponder before we go.
Oh, this is a good one.
We noted that this entire memory system, these highly refined SOPs and strategic paradigms, is stored in plain text.
Right.
It is LLM-agnostic. And we know that an AI can easily share this text-based memory with another AI just by letting it read the file.
Just handing over the manual.
Exactly. So what happens when an entire network of AI agents deployed across a massive corporation shares a collective brain for a year?
The compounding knowledge would be staggering. I mean, every mistake made by one agent instantly becomes a learned lesson for every other agent in the network.
Are they going to autonomously generate, refine, and seamlessly share the ultimate flawless corporate manual?
It's very possible.
And eventually, will human employees be asked to study the workflow handbooks written by the AI because the AI found a more efficient way to do our jobs?
Now that is something to think about.
It really is. Thank you for joining us on this deep dive into the MUSE framework. Keep learning, stay curious, and maybe tomorrow morning when you open your laptop, be thankful that you don't have to relearn how to use your email from scratch. See you next time.